So again, I'm going to go back to Calc 1. I'm going to ask you a question that we've answered before. How does chain rule work? Here is f of g of t, a composite function, a composition. How do I take the derivative? Man. Now, if you took Calc 1 with me, you saw my lovely little nesting dolls, where you're like, oh, there's something on the inside. And if I want to take the derivative, I take the derivative of the outside. Oh, yeah. Then I have to take the derivative of the inside. I didn't bring the nesting dolls, but I had these with me. Great. Wonderful. Take the derivative of the outside, leave the inside alone. Take the derivative of the inside. But what if I don't just have one inside? I have two inside. Crap. All right. So let's suppose that our x of t and our y of t, those are the internal variables, but they're in terms of something else, right? They're in terms of this third variable t, a parametric equation. Okay. All right, wait a minute. If I have x of t and y of t, that's a graph. That's a parametric graph, right? So if I want the derivative, instead of saying I want the derivative in the x direction or the derivative in the y direction, I can say I want the derivative in the t direction as I go on this curve. The df dt, the derivative of f in terms of t, that gives the change in z as we go in the direction of t increasing along our curve. That sounds like an absolute space cadet of an idea. But let me draw the picture again. Here's our parabola. I'm going to draw a curve. Now, if I were truly spear bald like Dr. Burns, I would ask you to draw it on my head. I'd use one of the erasable markers we draw on my head. I still have bugs here, so I'm not going to worry about it. But let's just imagine we were going along some path on this surface. Or I look down from above and I see that path. Am I going uphill or downhill as I walk along that curve? Rather than, am I going uphill or downhill in the x direction? Am I going uphill or downhill in the y direction? Now it's, am I going uphill or downhill along this path? This theme is very weird. So let me set up a picture. Z equals f of xy equals x squared y minus, I'm sorry, plus 3xy squared. X equals sine of 2t, y equals sine of t. Now, before I do anything else, I want to graph this so I can try and get an intuition for what's going on. So I'm going to fire up the grapher, and then I'll share it so it'll go onto the recording. 3D graph, white, share that in Zoom. Here's my graph. Okay, so I'm going to put our equation. Z equals x squared, not capital X squared y plus 3xy squared. This is my hyperbolic paraboloid weird. Oh, that's a weird shape, isn't it? Let's change the colors because I don't like having that checkerboard on it. So I'm going to change the colors from checkerboard to solid. We'll just make it green again, and that's fine. Okay, so here's this, right? But now I need that x of t, y of t. So let me graph a new item, new equation. We'll make it a three-dimensional parametric curve. But I'm going to set z to be 0. So that we're looking at it in the xy plane. XYZ equals. Now we had x was sine of 2t or sine of t? Sine of 2t. Y is cosine of t. I was supposed to have cosine of t. I'll write it as cosine of t, and then I'll go back and I'll change it on the paper. And z is 0. So this is going to create a two-dimensional curve as t goes from 0 to 2 pi. It's kind of hard to see, but there it is. And if I turn off the surface, I can see it better, right? So we have this two-dimensional bow tie path in x and y. And now the question is, as I walk along this curve, am I going uphill or downhill? So I need you to imagine, and this is the hard part, we're going to take this curve and move it up or down until it hits the green surface. So this loop that's visible right here is going to kind of get smeared up here. Not exactly easy to visualize, right? Let me actually draw it. Equation, duplicate, there. So this time, instead of just having 0 for the z here, I'm going to change that to be x squared y plus 3xy squared. But I'm going to use the t's things, right? Now this is going to be long and ugly because it's not short. We have x squared, so that's sine of 2t all squared times cosine of t plus 3 sine 2t parentheses cosine of t squared. Let me put that on the outside of the square. There, right? Now, I could have just done that the first and then taken the derivative in t, right? So I can take the derivative of that. That's going to be a double product rule and two chain rules, and it's going to make my head explode. I don't like it. But now you see how that gets moved onto the surface. Let's change the color so it isn't the same as the other color. We'll make that one inspector. We'll make that one purple. No, it's too hard to see. We'll make it red. There, now it stands out. Turn off the inspector. So you can see how the red curve is basically the blue curve, just going up and down as well as going from side to side. right? And now the question is, as we move, wherever we are we going uphill or are we going downhill? On that surface. I promise I will post this file in Grapher so you can play with it more. Stop share. Okay, I got to go back here. That's not supposed to be sine. That's supposed to be cosine. Now, I could say I want to find dz dt, and I could take this for t and this and plug it in and write that all out, right? That's disgusting. That is just nasty and I don't want to do it. So how can I do it without this? Well, let's think about the chain rule. Chain rule says take the derivative of the outside, leaving the inside alone. But the inside is two pieces. Z has both x and y in it. So if I take that, it's not a regular derivative. It's a partial derivative. If I take the derivative of the outside, it has to be a partial derivative. Because there's both an x and a y. I have to do the partial with respect to x and the partial with respect to y. Right? But then I need the derivative of the inside. The derivative of the inside needs to get multiplied on. But it needs to get multiplied on the correct inside part. So I would say, oh, I'm going to get the partial of f with respect to x. And then I'm going to multiply that with the derivative of x with respect to t. That's the derivative of the inside. Notice that's a regular derivative because x only has one variable in it. X only has t in it. It doesn't have anything else. What do I get over here? I get the partial of f with respect to y, and then I'm going to multiply that by the derivative of y in terms of t. Which means my chain rule actually splits down these two paths. And to do dz dt, I do partial of z with respect to x times dx dt, and I have to add partial of z with respect to y dy dt. And that means I know how to do this. I now know how to take the derivative I want. Problem. The resulting expression is going to contain three variables. It's going to contain x and y and t. So going back to our equation up at the top, where z is x squared y plus 3xy squared, what's partial of z with respect to x?
So it's y plus x y squared.
Careful.
Sorry, 3y.
And partial of z with respect to y.
Squared plus 6y. X.
The x is as much of a number as the 3 is in terms of y. Oh, wait a minute. We also had x was sine of 2t and y was cosine of t. So I can get the derivatives of those pieces as well. What's the partial of x with respect to t? Sorry, not partial. That's regular derivative. That's dx dt and dy dt. What do we get for those? And the root of cosine. And so now I multiply and add to put all these pieces together. To do dz dt, I write out partial with respect to x, 2xy plus 3y squared times the derivative of x with respect to t. Then I add, write out partial z with respect to y, and multiply by the derivative of y with respect to t. An expression that happens in 3 variables. Now, an interesting note. Kind of hard to see, but that's our blue curve. Let me zoom in. That's our little blue bow tie shape that we were looking at in the other picture, right? That's the flat one in x and y. I graphed it in our parametric equations. Set 0 to 2 pi. That's exactly what we want. When t is 0, I am at this point right here. T equals 0, x equals 0, y equals 1. And as t increases, as t gets bigger, x gets bigger. So I'm going this way. We go back to that picture in 3D. Am I going uphill or downhill? I'm at this point. I'm going to the right. I'm going uphill. If you put in 0, 0, 1 to this, put in these numbers to this, what do you get? Well, I'll have to save it later. I just hit save and it went, oh, so let's try that again from here. Nope, we're gonna leave that for now. So what do you get when you actually plug in? When I plug in 0 for x, 2xy is 0, 3y squared, because I plug in 1 for y, that's 3. 2 cosine of 0. What's cosine of 0? 1. So that's 3 times 2 times 1, that's 6. Plus 0 times anything is 0. I get 6. My slope is positive. My slope is positive means I'm going uphill. When I walk along this direction from this spot, I am going uphill. Fairly steeply, I might add. For every 1 foot forward, I go 6 feet up. That's a really steep slope. It's almost a climb up a ladder, isn't it? But this is what a derivative means. It's a rate of change. But now I don't just have the rate of change in the x direction or the y direction. I have the rate of change along a curve. By the way, this applies not just to functions of two variables, but functions of as many variables as you want. If you have f of x1, x2, up to xn, where x1 is a function of t, x2 is a function of t, and all of these are functions of t, then I can do the same thing. And I can say that to do df dt means to do all the partials. Partial of f with respect to x1 times dx1 dt all the way up to partial of f with respect to xn times dxn dt. But in my head, I like drawing a little picture. The tree that I drew earlier. I think of f, and f has all these variables in it, right? So I think to myself, up here, I'm going to write f, and I'm going to write x1, x2, dot, 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 xn, and then I'm going to think about t inside all of those. And now here's how that helps me. I have to multiply down the branches. And every time I have a branch with more than one thing coming out of the root, I do a partial derivative. And every time I only have one coming out, that's a regular derivative. So I'm going from f to x1, that's a partial. I go from x1 to t, that's a regular. That little tree reminds me of doing probabilities and conditional probabilities and all that crap. And all of a sudden it's like, oh, a same tree diagram. I've seen this before. If you haven't done probability, you're looking at me like this tree makes no fucking sense. I promise. Every time you split, do a partial. Every time you don't split, do a regular derivative. That's exactly the way to build this one. Which means I can do it in 3 variables. Why would I be doing this in 3 variables? I actually have an application here. When you fly a plane, the temperature changes. Temperature on the ground versus temperature up in the air is very different. But as you move, not only does your temperature change, the wind speed across you changes your temperature even more. The size of the plane physically changes. Metal expands and contracts in temperature change. I want to know how much bigger my plane is on the ground than it is in the air. Change in temperature as I fly through the air. Well, that's going to depend on the temperature at every given point, isn't it? The temperature is a function of 3 variables here, or more if I think about wind speed as well, right? All of those things. And now I'm moving in some path around the globe. What's the change in temperature as I keep flying? It changes how tight the bolts are on my plane. It changes how tight the panels hold on to each other because they shrink slightly in the cold and they might rattle a little bit. You've gone on planes, you've listened to the windows rattle as you fly around, scared the bejeebus out of me. But the increased pressure inside the tube, because the decreased pressure outside, holds it all together another way. So there's all these different variables involved, and then I'm moving. How does it change as I move? Okay, that's a really, really weird example. I'm going to give you a case where it failed and was a problem. Measuring the temperature of the surface of the plane, the wing of the Challenger, the space shuttle, was damaged on takeoff. And it wasn't until landing that the temperature became an issue and the heat shield was fractured and it ripped the wing off the plane and killed the astronauts. It's this sort of question. Useless stuff, I'm never going to care. People died. I don't want that to happen on my watch. Questions?
Like, what if there's a, change based on change?
So now I'm going to have to ask, are you talking about a second derivative? Then yes, I can do that second derivative. Absolutely. I'm doing a second derivative in t, right? So I'd be taking the derivative of this with respect to t, which means now this is a 3-variable expression. So I do the derivative with respect to x, that's got partials. The derivative with respect to y, that's got partials. The derivative with respect to t, that's got partials. But then I need these pieces, and that has dx dt and dy dt. But there is no dt dt, is there? I most certainly can do a second derivative. It's just more of the same and uglier. Because now I'm in this condition, but I have x, y, and t. So I do the partials for the first 3, but when I do dt dt, I get 1. I can do as many derivatives as I want. I don't want to do that many, but I can. Other questions? Yeah, yeah. I have to know the path I'm following to be able to take the derivative along that path. Yeah, if I don't have x and t and y of t given to me, how do I know which way I'm going? More questions?
Can you just say the thing again about the, when to use what?
Okay, whenever there's a branch that splits, do partials. Whenever there's no split, regular derivative. I like this idea. But of course, this is version 1. Because the problem is that f depended on x and y. And x and y only depended on t. No rule says these have to be 1-variable functions either. What if instead of x of t and y of t, Nora, I give you x of s and t, y of s and t? You nasty mother, why would you do that to me? Because now, Jack, I'm going to take my picture and I'm going to figure out what happens in my tree. What would be different in this case about my tree?
No, it would be like, it would go partial.
So from f, I go to x and y, and those are partials. But from x, I go to s and t, which means those are partials. And from y, I go to s and t, and those are partials. There is no other layer because there's nothing underneath that, right? There's no other variables involved. So that's as far as I need to go. But now that means all my derivatives are partial derivatives. And really, I'm going to try and figure out the change in f with respect to s. And if I'm following that set of branches, I have to follow it down to the s's. And that means that every one of my derivatives is a partial. It's partial of f with respect to x, and then partial of x with respect to s. But it's also the right-hand branch, partial of f with respect to y, partial of y with respect to s. But that's only one of them. Because I have an s, I also have a t. I could follow the same set of branches down to x and y and then go the other way to t. And, you can have as many variables at every layer as you want. You could have f have x, y, and z. You could have x have, I don't know, r, s, and t. You could have y have r, s, t, and w. Well, then really I'm thinking that there's a w over here. It's zero, right? You just have to take all the branchings. Trust me, draw the stupid tree picture. It helps so much. I didn't do this randomly. I did steal one from the textbook. F equals arctangent 2x plus y, where x is s squared t and y is s log t. Isn't that just disgusting? Again, if you really wanted to, you could take this expression for x and this expression for y and plug them in over there. And then just do the derivative with respect to s and the derivative with respect to t. And this is small enough that that would work. It sure as hell ain't pretty, but it works. But I think this is actually easier to do in this case. My problem is that my resulting expression now has 4 variables in it: x, y, s, t. Phooey. Let's give it a whirl. Tell me what you get for the partial of f with respect to s. First thing I need to remember is what's the derivative of the inverse tangent? There was a formula sheet on our first exam, simply because I didn't remember it either. Right. But this is arctangent of stuff, so it's 1 on 1 plus stuff squared. So derivative of f with respect to x, 1 over 1 plus stuff squared, derivative of the stuff. What's the derivative of 2x, y, 2x plus y with respect to x? Just 2. So that's partial of f with respect to x times partial of x with respect to s. What's the derivative of x with respect to s? Plus the derivative of f with respect to y. 1 over 1 plus 2x plus y quantity squared But wait, there's more. What goes inside this set of parentheses? Just a 1. And now partial of y with respect to s goes there. What's dy ds?
Or
Presto. Best part. If I want to do the derivative with respect to t, neither of these change. Only those change. Because when I go to do partial of f with respect to t, I still need partial of f with respect to x. But now I need dx dt. What's dx dt? I did it again. What's partial x with respect to t? I keep saying d, even though that's that partial symbol. It's a habit I've been doing for way too long. Partial of x with respect to t. And the other part, 1 plus 2x plus y quantity squared times 1. Now I need the derivative of s log t with respect to t. What's the derivative of ln of t? And therefore the s stays with it. And I get s on t. This does not have as pretty of an image as the other one did, because now each of x and y are two-dimensional controls. I'm not walking along a path. I'm like walking on one surface and measuring something else, walking on another. These are much more complicated visually. They don't work the same way. When it's a one variable middle step, that's easier to visualize. You asked about second derivatives. Example 7, page 941 is about second derivatives. And that's all I have to say about that. Bleh. Questions? I would point out to you, I've done one example of each, but it's not any new derivative rules. It's just a new way of keeping track of what we're doing for derivative of the inside versus derivative of the outside, whether we do a partial or a regular derivative. And that depends on the way the variables are related. But let me go back to something we mentioned on Monday about implicit derivatives. I think the equation we were using was like that. And we talked about doing the derivative with respect to x and the derivative with respect to y and all of that junk. If I think of z as a function of x and y, then we can do what we did on Monday, and you just use the partial derivative. And remember that whenever you take a derivative of a z, you get this extra thing. But let me think of this whole thing as a function of 3 variables. What is partial of f with respect to x? Notice I'm using the capital F. So I'm thinking about this just as a single variable function, a 3 variable function. No chain rule required here. I don't want to think about the chain rule for the moment. Let's just think about the regular derivative with respect to x. What do I get? Okay. What if I do the partial with respect to z? Okay. Let me go back to Monday's notes. Over here on the left, let's do this like it was the chain rule with the hidden idea. If I want the derivative of z with respect to x, then I need to take the derivative of everything in terms of x and keep the headspace that there are x's hiding inside of z's. That's where we used the chain rule from Calc 1. So when I do the derivative of x cubed, I get 3x squared. When I do the derivative of y cubed, I get 0. When I do the derivative of z cubed, I get 3z squared partial of z with respect to x. And then when I do the derivative of 6xyz, I got to do the product rule. So I get 6yz, because the derivative of x is 1. And then I get 6xy dz dx, right? And this is exactly what we did on Monday. And then we rearranged to get dz dx alone, right? I'm going to do that right now. So let me do that right now to solve for the other side. This was equal to 0. So I'm going to move the non dz dx terms over. So I get 3z squared dz dx plus 6xy dz dx equals negative 3x squared minus 6yz. And then if I factor out the dz dx, I get 3z squared plus 6xy. Hang on a second. 3z squared plus 6xy. Minus 3x squared minus 6yz. That's the negative of that piece, isn't it? To get dz dx, it's minus fx over fz. When I write an implicit function, I can think of it as a quotient of partial derivatives. The chain rule gets vanished. Implicit functions are nicer to deal with because of this. And that's why all of our quadric surfaces were written either z equals explicit function or implicit x squared, y squared, and z squared. Because I could do the derivatives this way. And I can think about moving on my surface now in an easier fashion. Guess what? It works the other letter too. As a matter of fact, this result is called the implicit function theorem. And one of the first results in proofs in calculus that I had to learn was the proof of this sucker, which isn't that long, but it's really messy. We're not going to do it. Page 943 works out an example for this in the same way in more generalized terms. I like the chain rule. To me, the chain rule is familiar territory because we did it a lot in Calc 1. But now that version over there with the implicit functions, I remember when we did implicit derivatives in Calc 1, and a bunch of you wanted to punch me in the head. But it's easier in Calc 3 terms. And that's really interesting. Because the partial derivatives gives us extra information. I wouldn't have had it. Questions? This also works for more variables. If you have a 4 or 5 function, 4 or 5 variable function, and you write it implicitly, it still works the same way. But that also means you could do dx dz, or dy dz, or even dx dy here. You can think of whichever pair of these and ask how they relate to each other. And that gives me, again, more information and more options. Questions? Perspective shifting like that. Instead of thinking of z as my dependent variable, think of y as my dependent variable, think of x as my dependent variable, is literally just returning the graph, so which one points up. So if I have z in terms of x and y, that's great. But if I do this, then I have x in terms of y and z. If I do this, I have y in terms of x and z. So I can redraw the picture and think of which one is up. And thus change the way I'm looking at this graph. There's no requirement that z is my dependent variable. It's just the one we use. Blame that on Pierre Fermat. It's his fault we use the letters at the end of the alphabet. Tomorrow is question and answer day. Friday, the homework is due, so I will see you all tomorrow. Have a wonderful rest of your day, everybody.